Okay, thank you very much. And first, I would like to appreciate Kazakhstan and because I have this opportunity to have the lecture here. And this is also today's an outline and the background method implementation and experiment. And then, so I will show the conclusion of our implementation. And the background is first, why do we choose and why do we use RISC-V processor? I would like to explain that. And about 20 years ago, 10 to 20 years ago, we were happy and believe a brilliant future because, some people say that Moore's law ends, but at that time, transistor number is increasing, and single cell performance is also increasing, and the frequency was also increasing, and we can, and so we expected the growth of processor, but because that scaling was boosted LSI performance, and probably you know the 変わってない。Okay, so sorry. Because the performance increase was boosted by the scaling. And probably you know the denied scaling. And if we follow this rule, we can easy to obtain the better performance compared with the previous CPU generation. So for example, if scaling factor is 0.7, then we can obtain the double performance of the previous generation. However, at that time, power consumption. Okay, so at the time, power consumption around performance growth. Please wait for a while. Sorry. Too many delays. So I found okay. So power around the growth. And sorry, yes, so can you accept the one single CPU power consumption is equivalent to the total of 3 to 5 microwave ovens? Probably, so we say no, because the 1 kilowatt is too large for one single CPU. And if that power consumption, so we cannot make the data center for the HPC and so parallel computing. Therefore, you can see typical power was saturated from 2005. And also frequency is saturated. And the 6-thread performance is also saturated. But if we focus on the number of logical cores, the number of logical cores is increasing because we would like to obtain the performance more. So we can say currently that's a CPU error enters the new edge, so multi-core edge, multi-core or many-core edge. Therefore, our laboratory focus on how do we use multi-core efficiently. So I would like to show the brief history of our proposed architecture. And around 15 years ago, so from 2006, our research was started. And in this time, so we use Super 8.2 architecture. This is a commercial architecture. And especially this multi-core processor is focused on extreme environmental embedded computing, such as satellite system and space systems. And Super 8.2 is a commercial architecture. Therefore, we can say this was a legacy architecture. And therefore, we can develop from scratch and prepared very good SDK, software development kit, and we can implement this on the FPGA. In industry, I think so. This was a success project. However, in academic, not so many people know the Super 8.2 architecture, so less interest. Therefore, we change from Super 8.2 to ARM9 processor. ARM9 is probably ARM processor is also and this is also one of commercial processor and probably is worldwide and very famous processor, embedded processor. And also this prepares good SDK, and we can implement this on FPGA because we developed this architecture, this design from scratch. But one barrier was intellectual property. So we developed from scratch. However, we cannot open this architecture in public. Therefore, we changed the architecture from ARM9 to original ISA. And at that time, we focus on the HPC, high performance computing. So no limitation, and especially we focus on the ASIC design, and that was our target process was 7 nanometer. However, one problem is that if we use original instruction set architecture and we propose original instruction set architecture, we must prepare the compiler and also some other development tools. So usability is extremely less than commercial processors. And also, cost is too expensive. Therefore, we move to back to FPGA. And currently, this project is continuing. And we also propose original ISA, and also this instruction set architecture is optimized for FPGAs. However, usability is still remains as our issue. And therefore, now we also use, and so we start a new project as a RISC-V architecture. And this is very well known, and very good point is also customizable processor. So, and also in this moment, we don't face any disadvantage using RISC-V processor. Therefore, my presentation is from the viewpoint of RISC-V user. So I would like to show one extension of the RISC-V processor. And therefore, I don't want to say many for RISC-V instruction set architecture. But one thing is, yes, you can see the table. So we can customize some instruction set, instructions. And this presentation, so I would like to explain and so introduce our customization of RISC-V processor. So, sorry for waiting. From now, so I would like to talk about some method. And yes, first, we introduce SIMD, SIMD architecture to RISC-V processor core. Probably you know the SIMD. That's so I would like to say again here. We use multiple RISC-V processor core. And in this example, 4 RISC-V processor was used. And one instruction sequencer issues one operation, one instruction string. And all RISC-V processor follows the instruction. But data was different. Data is so different. This is a overview of SIMD, parallel architecture. And if we use RISC-V core, I said so we extend instruction set. Therefore, we introduce SIMD. So we extend the instruction set and this is the open code of our instruction. And for this manner, expected application is one is matrix multiplication and AI application, database search and scientific application, and FFT. FFT is also widely used in image processing, signal processing, and others. Therefore, in this time, so I would like to show how our proposition is work efficiently in FFT. And the FFT is also maybe also you know the very famous application. And we implemented radix 260.DIF FFT. And if we write the diagram, you can see the slide. This is FFT diagram. So then, if we accelerate this computation, we should accelerate a single butterfly operation. So if this is implemented on SIMD architecture, FFT requires complex floating point arithmetic and multiplication with 12 factors, and group addition and subtraction, and 4-stage butterfly operation. If we implement it, and so if we can do these we can respond these requirements on SIMD architecture, it's our goal of this slide. And okay, and this is our RISC-V implementation. And first, focus on the complex floating point arithmetic and multiplication with 12 factors. Then, this computation is realized independently. So it means we can implement this computation on different processing elements, so different RISC-V processor. But the operation is same. For example, C0 and C1 was calculated like this. we use so FMRS and FM server and so FM ads. So this can be done, and this requirement done by RISC-V instruction set architecture. And also, we can easily to extend SIMD manner. And the next is group addition and subtraction. So if we talk about the group addition and subtraction, this computation is also calculated independently. Therefore, this computation is also easy to extend to the RISC-V with SIMD manner. However, the next 4-stage butterfly operation has some problem. Because addition and subtraction have to be executed in different clock cycles. So stage 1, stage 2, stage 3, stage 4, we can see. But each stage includes 2 operations. We cannot do 2 operations at the same time. For example, so in stage 4, nth clock cycles. Please wait for a while. Yes. So nth clock cycle. So we can do addition. And the next clock, we do the different subtraction. But both cannot be executed in the same clock cycle. So it means the efficiency is half of ideal performance. It's not good for multi-core and many-core processors. Therefore, we propose the DIMD, Dual Instructions Multiple Data Stream Architecture, DIMD architecture. This is also motivation. And if we issue the 2 instructions, like instruction 0 and instruction 1, then we can use all processing elements efficiently. So, for example, not only stage 4, stage 1 to stage 4, or all stages, we can use all processing elements. All computation can be calculated at the same clock cycle. That's a big difference from SIMD architecture. Therefore, we propose DIMD, and also we use RISC-V ISA because we can add our original instruction set, instructions. And in DIMD architecture, if we use the DIMD architecture, we can easy to exchange the data between adjustment PEs. So, for example, if we use SIMD architecture, in the first clock, we need to move the data from left to right, and then right to left. So it means that at least 2 clock cycles was required. But if dual instruction stream, we can swap, we can exchange the data only 1 clock cycle. So this is our motivation and overview of our implementation. And then, sorry, yes. And this is our DIMD-based RISC-V architecture on FPGA. This is the overall structure of the architecture N/M RISC-V-based P-array. And this architecture is composed of P-array and instruction sequencer and other modules like memory controller and including DMA and some. And instruction sequencer has 3 memories. And one is instruction 0, so instruction memory. And the other is we introduce a mask operations. What's mask? For example, FFT implementation. For example, FFT implementation, we please see the right figure. In stage 0, upper half and lower half is adapted, so different operations. But in stage 2, add low and low, even low, that's different operation. Stage 3 is left half and right half is different. And stage 4 is even column and odd column is different. So we can, we introduce two dual instruction set architecture. However, we need to change which part and which column was adapted to instruction 0 or instruction 1. Therefore, mask decided that which operation was adapted or not. And this this is our current mask code pattern for DIMD-based architecture. For FFT, we only use row-based mask and column-based mask. However, if we focus on the AI, especially the convolutional neural network, we need to use other masks. Therefore, we already introduce these masks for other advanced computation. And from next slide, I would like to talk about the datapath, network topology. And this is our topology. And one RISC-V core has 6 paths in total. 4 for the adjustment interconnection. You can see the 4 red-colored connection. And the other 2 is for distant interconnection, green-colored connection. This topology accepts higher structure, such as 5-cube interconnect by using red connection, like this figure. And therefore, we use this connection, and we also say a tightly coupled architecture is this. And in this neighbor communication, we prepare the neighbor instructions. This slide shows the neighbor instructions. And this is the base instruction format for neighbor communication. And the opcode is 11010111, and we can choose the how do we exchange the data following the manner, direct manner. For example, in for example, this is our neighbor instruction, and focus on the function 7. We can choose we can choose the equivalent. If function 7 is 0, then we choose just direct neighbor communication. But function 7, so we choose distant neighbor communication. And if we change the mutual change bit, if this bit is 0, if this bit is 0, we follow the SIMD manner. However, if this bit is 1, then we can exchange data between the neighbor processing element. And this is our basic core of RISC-V. And we follow, we use E203. This is a famous Chinese core called Hummingbird core. And we choose this core is very good for us. But if we find new different core, we would like to challenge to implement our method on the new core. But anyway, so in this time, in this presentation, we would like to show the performance of this core and our proposition. I'm sorry, too big delay and okay, and this is experimental result, and we use Xilinx Syntax ultra-scale FPGA, and all circuit was written by Verilog HDL. We don't use any OpenGL or C code or high-level languages. We use Verilog HDL, and RISC-V core. For RISC-V core, we use assembly code because in this moment we cannot prepare the good compiler for DIMD manner. And one thing, I would like to say the right table show our pseudocode of FFT, and all gray colored code. So, for example, in stage 1 is 34 and 38. You can see the two operation in the two columns. Instruction stream 0 is F at S, but in instruction stream 1, F sub S. And all gray colored code runs as DIMD. And around 1/4, 26% were DIMD instructions in FFT implementation. This is okay. This is performance comparison. 6-point FFT. So in SISD, we analyze the detailed results. Then in SISD, the implementation runs on a single core. Thus, the cycle was divided by 64, and therefore memory access consumes clock cycles instead of data exchange. SIMD is has a bottleneck. It's from neighbor communication for data exchange. In DIMD, DIMD could achieve good performance around 2.2 and so 1.1 times speed up compared with SIMD and SISD computation. So we could achieve the good performance, but circuit usage is almost the same. This slide shows the circuit usage, resource usage comparison. The DIMD, SIMD, and SISD is almost same. Therefore, we think this is good, good extension of one RISC-V ISSA, and also I would like to talk about the scalability of DIMD architecture. And yes, this is the difference. So we prepared and so we implemented the 4 different designs for DIMD, 1 by 1, 2 by 2, 4 by 4, and so 8 by 8 implementation. But you can see this result shows a good scalability without any overhead. Therefore, I think we think this implementation is good for many core architecture, and also this implies 16 by 16 implementation without any special techniques. And if we customize some special circuit reduction method, then we can implement it to 60 by 16. So in total, 512 processing elements can be implemented on one single FPGA. This is the conclusion. Multi-RISC-V with advanced SIMD architecture, so we propose, and this achieves good parallelism, and also good stability from 1 core to 64. And therefore, I think RISC-V core is a very good, good core and a good candidate for our embedded and also HPC architecture design. Thank you very much.
Thank you for Mr. Yamaguchi.
Okay. Thank you very much.
Thank you. And it's time is over, so only one question can I ask. And this question is, do you consider implement the P extension of RISC-V? Would it be better performance with P extension?
Pardon? Excuse me. So,
do you consider from audience chat? Do you consider implement the P extension of RISC-V? Would
yes.
it be better performance with P extension?
Yes.
Okay. Yes. Your answer is yes.
Yeah. So if we use the extension, then so we can customize and optimize the architecture ISA to our target application.
Okay. So time is up. So thank you so much, Mr. Yamaguchi, your presentation. Thank you.
Thank you very much.